All right, so maybe let me uh, do some examples. Let's consider again the standard metric space, real line with the absolute value metric. And let's consider this subset. Okay, -2, 5, and then uh, okay, 9, 12, and then 25, let's say. Let's consider interior, exterior, and all that stuff for this set. What is, for example, interior points of A? So we have to consider points so that I can draw a ball around that point, and that ball will lie completely inside A. I can certainly do this for any point between -2 and 5, excluding -2, because if you draw any ball around -2, some part of it will be contained outside of A, certainly. So I have -2 up to 5, and this is already open. So I have this, and it seems that's it, right? This is the largest open set contained in A, right? Largest open set contained in A. What about exterior of A? Well, it should be the largest open set contained in X minus or R minus A. Largest open set contained outside of A. So it is minus infinity up to -2. Since it is open, we should have like this. And then 5 to 9. And then uh, 12 to 25. And then 25 to infinity, right? So this is the largest open set contained in R minus A. All right, what is left for the boundary? Okay, so I have -2, 5, 9, 12, and 25. Right, just 5 points. -2, 5, 9, 12, and 25. All right. Now, any questions? Okay. Now consider the following metric space. Let S be the subset 0, 1, and consider BS the with the submetric, the metric space of bounded functions on 0, 1. Okay, on 0, 1. Now I will recall some information from your first year calculus course. In this course, we will also define continuity and everything, but just, for the sake of this example, recall the following. Recall from first year calculus course that any continuous function f from a closed interval into R has a maximum and minimum, right? Has a maximum and minimum. Later, actually, we will prove this. You have seen this theorem in first year calculus course, but you didn't prove it actually. We will prove this theorem, but for the sake of this example, just, accept this. Well, any continuous function has a maximum and minimum, and therefore it is bounded, right? So if it were not bounded, then it wouldn't have either maximum or minimum. So since it has maximum and minimum, it must be bounded. In particular, f is bounded. Hence, the set of continuous functions uh, on 0, 1 is contained in BS. So this is what I'm saying. Let's say the set of continuous functions on 0, 1. So what is this? This is the set of functions such that f is continuous. Okay, continuous. So continuous functions, and we know that continuous functions CS, maybe I should say, S is just the 0, 1. So this is contained in BS. Okay, we may ask the following. Well, this is a subset, so I can ask whether it is closed or open, or what's the interior, exterior, and so on, right? Do you have any guess whether the set of continuous functions is open or closed inside all bounded functions? Do you have any guess? Continuous functions, would it form a closed set or an open set, or neither? Okay, claim is this. Uh, this is a closed set. How can we see this? I will make a proof using pictures. I will not give a detailed proof. Detailed proof will be given later, just for the sake of this example. This is a closed subset, and the proof is the following. BS minus CS is open. So what I claim is that the set of discontinuous functions, right? If I subtract continuous functions from the set of all bounded functions, what is left? The functions which are not continuous, right? And I claim that functions which are not continuous are not uh, closed. Actually, it is open. I shouldn't say not closed. This is open. Why is that? It's very easy. You see, uh, I can draw actually real picture in this case. Okay, let's say. So I am looking at the 0, 1 interval and all continuous functions or bounded functions on this interval. I claim that this set is open. So if I take an element here, an element like here means what? It is bounded but not continuous. Well, a function like that would be, I am. This is just, a picture. For example, this is a function like this, right? F here is bounded but not continuous. Now I can find a ball around this function which is contained again in BS minus CS. So I will find a ball around F so that all the functions in that ball will be bounded but not continuous. How can I do this? Well, you see, I will look at the jump here, right? There is some jump here which results in discontinuity. I take a, neighborhood of this, an epsilon neighborhood, so that, okay, so something like this. Okay, so I take my epsilon so that the distance between f and okay, so I choose my epsilon so that epsilon is smaller than half of the distance, the jump here. So if I drove the epsilon ball around f, uh, there will be still a gap at this point. So uh, so this is my epsilon. Okay, this is my epsilon. This is my epsilon. Now if I choose any function in the epsilon ball around f, I will have what? So okay, if I choose a function in the epsilon ball, it means if I choose a function whose graph lying inside this red region, red, lines, curves, I will get something like this. And you see, the other end will start from a point in this interval, and that interval and this interval has no intersection. So no matter where it starts, okay, it cannot be continuous because these two intervals has no common point. So there is no way you can connect this endpoint to this endpoint because they lie in disjoint intervals. So therefore this G, whatever it uh, is in BS minus CS. In other words, the ball around F, this discontinuous function with radius epsilon lies inside BS minus CS, and therefore, you know, BS minus CS is open because it contains a ball. Okay. This is of course not a I mean complete proof, because you know this is just an example of a discontinuous function. How do we know that all discontinuous functions look like this and so on? But this gives a very nice idea how this uniform metric looks like, how balls looks like, and so on. Also, you should keep in mind that the set of continuous functions usually form a closed subset. Okay, in this case it is closed. There we will see many other examples where the set of continuous functions are always they form a closed subset. All right. Do you have any questions? Okay. Now let's see uh, another uh, topic. Sequences in metric spaces. Actually, this will be very similar to our discussions about sequences in real line. Right there, we had many, facts. Either we proved them or stated them. We gave many definitions and so on. We will just extend all that stuff to arbitrary metric spaces. Uh, but always keep in mind or think of the analogies between this and the real line, and sequences also in metric spaces and sequences in real line. Uh, most of the time they will be parallel, but there will be some essential differences. Okay, so let XD be a metric space. A sequence in X is a function, f from X to R, X to R, no, sorry, from N to R, X. Right, function means sequence means the function from natural numbers to X. Right. Usually we denote the image, the value fn as f sub n, right? And write fn to denote the function or sequence. We don't write a sequence like this, f, a function from n to x. We simply denote it this way. So in other words, we just list the values of the function, right? Fn is just f of n, the value of the function at n. Okay, we can do this because natural numbers is countable. That's the reason. Okay, now what is the next thing? We have sequences. Now we will define, of course, convergence sequence. Okay, definition. Let xn, so in this case, from now on, our sequences will be either xn, an, and sometimes we will write fn, especially when we talk about uh, uh, matrix spaces consisting of functions, like the above example, there are uh, elements are indeed functions, right? So we will use this notation, but usually we will use either xn or an. Okay, so let this is a this be a sequence in xt. We say that xn is convergent. Xn is converges to some uh, element x in x if what happens if for any epsilon positive there is uh, some and 0 so that n greater than n0 implies distance between xn and its limit. Well, in this case I cannot use absolute value. I will just use its analog in the metric space. Distance from xn to x is less than epsilon. Okay, so the same uh, definition we had for real numbers and sequences in real numbers. The only difference is that instead of absolute value of xn minus x, right, we would have that in that case. Instead of this expression, I have its analog in a metric space, which is the distance function from xn to x. Okay. In this case, of course, again we write in this case, we write limit xn is equal to x as usual, okay, as before. All right. What else should we do? Uh, Again, we have the similar fact that limit point of a sequence is unique. So let me write as a proposition. Recall that in case of real numbers, a sequence may have at most one limit point. The same holds for sequences in an arbitrary metric space. So any sequence xn can have at most one limit value, one limit. And the proof is the same. So let's uh, assume that limit xn is equal to x and limit xn is equal to y for some xy in x. What I have to do, I have to show that x equals y, right? So we must show x equals y. All right, how can I do this? Well, let epsilon be given. then epsilon over 2 is a positive real number, and I apply the definition of limit point to both limits. Then, so by the definition, definition of being a limit point, there is some n0, but let me say n1 because I will need another one for the other limit, so that n greater than n1 implies distance from xn to x is less than epsilon over 2. Well, I have also this fact, right? Limit xn is equal to y. So I can find another n1. Similarly, since limit of xn is equal to y, there is some n2, not necessarily the same index, it might be different, so that n greater than or equal to n2 implies distance from xn to y is less than epsilon over 2. But now I can use triangle inequality. How? Well, uh, consider a natural number which is larger than both n1 and n2. So let n0 to be the maximum of n1 and n2. Then this distance x n0 x is less than epsilon over 2, and this distance, well, this point is epsilon over 2 close to both x and y. So the distance between x and y cannot be larger than the sum of these two distances, because I have a triangle like this, right? Here is x and 0, here is x and y. So this distance cannot be less than the sum of the distances. Hence, by the triangle inequality, we get what? Distance from x to y is less than distance from x to x and 0 plus x and 0 to y. But this is less than epsilon over 2, and this is less than epsilon over 2. So this is less than epsilon. So what we obtain is this. This distance, which is always positive because metric never takes negative values, and this is less than epsilon. What was epsilon? Epsilon was an arbitrary number where uh, arbitrary. What is the real number which is non-negative and less than all positive numbers? Well, that is only 0, right? Hence, dxy is 0, or equivalently x equals y. And this finishes the proof. Okay? Okay. Evet. Aha. Şık olmaz. O yüzden hani dönüp onu düzelteceksin. Tamam mı? Ee, yani e, tabii ki epsilon'u ne seçeceksin? Epsilon 2 mi seçeceğiz? Epsilon bölü 3 mü seçeceğiz? Bazen işte 4 mü seçeceğiz? Bunlara baştan karar vermek kolay değil. Bunu ilerlerken göreceksin ama hani dediğin gibi yapabilirsin. Epsilon alırsın. Geldin baktın ha, epsilon çıkmadı da 2 epsilon çıktı veya 3 epsilon çıktı. O zaman döneceksin diyeceksin ki ya tamam ben epsilon almıştım ama bunu epsilon bölü 2 yapayım. O tip ayarlamalarla düzeltebilirsin. Yani sonuçta epsilon'u elde etmek zorundayız. Ee, ya şöyle dediğin doğru olabilir ama yazarken öyle yazmıyoruz. Yani e, çünkü o tip şeylere girersen hani onun bir yerde nasıl diyeyim sonu yok. Hani ha bu da olur, bu da olur dersen bir yerden sonra ipin ucu kaçabilir. O yüzden hani e, yani gerçekten onu epsilon'u çıkartabilmen lazım. Eğer hani baktın ki yani epsilon'a hiç benzemiyor. Belki o zaman hani dönüp şeyi yapman gerekebilir. Hani başka bir teknik bulmalıyım diyebilirsin. Yani genelde o tanımlara şey yapmak zorundayız, uymak zorundayız. Öbür türlü çünkü takip etmesi çok zorlaşır ve hani o yüzden de kabul edilmez o tip ispatlar. Şey değil. Uh, do you have any questions? Uh, remember also that we had facts like any subsequence of a convergence sequence would have the same limit, right? Metric space in the metric space real numbers. The same holds here. So similarly, we have the following proposition. Okay, so let XD be a metric space and Xn a sequence in X with, let's say, limit Xn is equal to X. Then for any subsequence X uh, Kn, we have limit xkn equals x. So the same statement we had for real numbers. Remember, what's a subsequence? Subsequence means the following. I have a sequence of increasing sequence of integers, right? So here kn's are integers. And I am just looking at the terms of the sequence starting with k1. So k1 xk1 and then xk2, xk3 and so on, right? I just pick some terms of the sequence. And our claim is that if xn has limit, then any subsequence you choose has the same limit. Okay, and the proof is very simple. So given epsilon positive, I am already given that limit xn is equal to x. So since limit xn is equal to x, there is some n0 with the following, so that n greater than n0 implies dxnx is less than epsilon. However, since kn is an increasing sequence, note that since kn is increasing, kn is always larger than or equal to n, right? Because k1 is at least 1, k2 is larger than that, so it is at least 2, k3 is at least 3, and so on. So kn is always larger than or equal to n. Hence, if n greater than n0, then kn will be larger than n, and that will be larger than n0. So if n is larger than n0 or equal to n0, then kn will be at least n0, so that this distance, since this index is larger than n0, this is less than epsilon. So what we have proved is then the following. Okay. Given epsilon positive, we found some n0, there is some n0, such that if n larger than n0, then this is less than epsilon. Well, this means that hence thus limit of xkn is equal to x0. Okay. Evet. Increasing. I'm sorry. Increasing. Actually, it is strictly increasing, but so what I mean is this: k1 is less than k2, k2 is less than k3, and so on, right? Therefore, kn is at least n. Okay. Well, we have sequences, we have convergence, limits, and so on. What else do we need? We need, of course, Cauchy sequences. So, and we have Cauchy sequences. All right, let me give the definition of Cauchy sequence. Again, the same definition. We just replace absolute value with the metric d. Okay, a sequence xn in x d is called a Cauchy sequence if what happens, if for any epsilon positive there is some, again, n0, so that m and n larger than n0 implies the distance between the nth term and the mth term is less than epsilon. right? The same definition, the very same definition. The only difference is that instead of absolute value, we have d xn xm. Okay, definition is the same, but we have a essential difference from the case of real numbers. In case of real numbers, convergent sequence and Cauchy sequence were the same, right? Any convergent sequence would be Cauchy, and we proved that any Cauchy sequence is convergent, meaning that the set of real numbers is complete. But that's not true in general for uh, metric spaces. So uh, okay, so uh, unlike the metric space, metric space, uh, real numbers with absolute value metric uh, in a uh, general metric space, uh, some the concepts of uh, being uh, convergent and being Cauchy are not the same. Uh, I will give an example. Maybe before the example, uh, okay, proposition. This part is similar. So uh, in any metric space, any convergent sequence is Cauchy. So if it is convergent, then it is Cauchy. There is no problem with this. And I will leave the proof of this as an exercise. Is left as an exercise. However, the other direction is not true in general. A Cauchy sequence may not be convergent, uh, as this remark tells us. So example, uh, consider the metric space uh, well, rational numbers with absolute value. Okay, rational numbers with absolute value, or okay, consider the sequence Rn in R in R uh, uh, in Q diyeyim, in Q rational numbers with limit Rn equals root 2. We proved at the beginning of the semester that for any real number, there is a sequence of rational numbers converging to that real number, right? Actually, we could take Rn as just the decimal expansion of root 2, right? R1 is the first decimal, so root 2 is something like this, 4 point, something like this, let's say. So I take R1 is just 1, R2 is 1.4, R3 1.41, and so on, right? Just each time I add one more decimal uh, to the rational number. Limit is of course root 2. So this sequence is convergent in R, hence is convergent in this metric space, real numbers with absolute value metric. Thus, this is Cauchy in R with absolute value. We just proved this. Any convergent sequence is Cauchy. But if it is Cauchy here, and thus it is Cauchy in Q, because if you write down the statement for being Cauchy in as a sequence of R and as a sequence of Q, they are the same, right? For any epsilon, there should be some index. After that index, the distance between the terms should be less than epsilon. So if this is Cauchy in R, then it is Cauchy in Q, right? There is no difference between these two definitions. So this is a Cauchy sequence. However, uh, however, Rn is not convergent in sorry, in this metric space. In the metric space, Q with absolute value. Why is that? Well, if it were convergent in Q, then of course it would be convergent in R, and its limit is just root 2. We know that limit is unique. Therefore, that limit value would be the limit value in Q also. However, root 2 is not a rational number, right? Uh, evet, is not convergent. Sorry. Convergent. And what is the reason? Sorry, let me rewrite it. Uh, if this is because if this limit, let's say R, uh, in the metric space, then of course uh, this would hold also in this metric space, because again the same definition holds, and the reason is that any rational number is already real, right? Uh, so this is since Q is in R, but then which would imply that R equals root 2, since limit of a sequence is unique, right? However, root 2 is not a rational number, and this is a contradiction. This would be a contradiction. Right? If this limit exists in Q, then this limit, of course, would be a rational number. But if we have this in Q, then the same holds in R, because everything here is every term here is also a real number. But if this holds in R, then this would be root 2, because limit of a sequence is unique if it exists. So root 2 would be a rational number, but that's not true. So in a metric space, in an arbitrary metric space, any convergent sequence is Cauchy, but there might be some Cauchy sequences which are not convergent, like this one. Okay, we have a Cauchy sequence and it is not convergent. And actually, we have a definition. So let me give this definition and I will stop then. A metric space, xt is called complete if every Cauchy sequence in xd is convergent. So if every Cauchy sequence is convergent, then we call that metric space complete. Example, we have already proved that real numbers with absolute value metric is complete, because any Cauchy sequence is convergent, and we just showed that and rational numbers with absolute value metric is not complete. Okay. All right. Do you have any questions? All right. Let me stop here then.